Every single second, Earth is under attack. Solar wind, streaming off the sun at over 1 million miles per hour. Cosmic rays from distant exploding stars, ripping through space at nearly the speed of light. Harmful ultraviolet radiation, pouring down constantly from our own star, energetic enough to damage DNA at unfiltered doses. The most dangerous share of that radiation isn't reaching you right now. And that's not luck. That's not an accident. That's a defense system. Before we go further, if questions like this keep you up at night, hit subscribe to Deep Space Files now, because this is exactly the kind of hidden science we dig into every single week. Earth is wrapped in a series of invisible shields, layered, overlapping, and almost completely invisible, that make the difference between a living planet and a sterile, radiation-blasted rock like Mars. So today, we are breaking down exactly what's protecting us, how it works, and what would actually happen if any of it failed. Let's get into it. Let's start with the outermost shield, Earth's magnetic field. Deep beneath our feet, Earth's molten outer core is constantly churning, generating electric currents through a process called the geodynamo. That process produces a massive, invisible magnetic field that extends far out into space, forming a protective bubble around the entire planet known as the magnetosphere. This field does something remarkable. It deflects most of the charged particles streaming off the sun, the solar wind, around the planet, rather than letting them slam directly into our atmosphere. You can actually see evidence of this magnetic shield doing its job. When charged particles do get funneled down toward the poles, where the magnetic field lines converge, they collide with gas in the upper atmosphere and light up the sky, creating the aurora borealis and aurora australis, the northern and southern lights. Beautiful to look at, but also a visible reminder of just how much energy is constantly being deflected around us. Here's where this becomes genuinely important, not just interesting. Mars is essentially a real-world demonstration of what happens without this kind of protection. Billions of years ago, Mars is believed to have had a global magnetic field similar to Earth's, but its smaller core cooled faster, and that internal dynamo eventually shut down. Without a strong magnetic field, solar wind was able to strip away much of Mars's atmosphere over billions of years, gradually stripping the planet of the protective, insulating layer it once had. Today, Mars still has some localized areas of magnetized crust, remnants of that ancient field, but nothing close to a global protective shield. The result is a planet with a thin, cold atmosphere and much higher surface radiation exposure than Earth. Earth's still active magnetic field is a big part of why we didn't share that same fate. Assuming particles to make it past the magnetosphere, they run into the second major line of defense, the atmosphere itself. Earth's atmosphere is thick enough to absorb and scatter an enormous amount of incoming radiation before it ever reaches the surface. This includes cosmic rays, extremely high-energy particles originating from sources like supernovae and other violent events across the galaxy. When these particles slam into atmospheric molecules, they trigger cascades of secondary particles, most of which lose energy and become harmless before reaching the ground. But there's one specific part of the atmosphere that deserves its own spotlight, because it handles a threat none of the other layers fully cover, the ozone layer. Sitting roughly 9 to 18 miles above the surface, within a region called the stratosphere, the ozone layer is made up of a relatively thin concentration of ozone molecules, a special form of oxygen made of 3 oxygen atoms bonded together instead of the usual 2. Its job is remarkably specific, absorbing the vast majority of the sun's harmful ultraviolet radiation, particularly the shorter wavelength UVB and virtually all UVC radiation, before it can reach the surface. Without this layer, that radiation would cause widespread damage to DNA in most living organisms, dramatically increasing skin cancer rates in humans and disrupting entire ecosystems, particularly the microscopic ocean life that forms the base of the marine food chain. This isn't a hypothetical concern, either. In the 1970s and 80s, scientists discovered that certain industrial chemicals, chlorofluorocarbons, commonly known as CFCs, were rising into the stratosphere and actively destroying ozone molecules, thinning the layer dramatically, especially over Antarctica. The global response is one of the most successful environmental interventions in modern history. The Montreal Protocol, signed in 1987, phased out the production of ozone-depleting chemicals worldwide. Decades of monitoring since then have shown clear signs of ozone recovery, with the Antarctic ozone hole gradually shrinking over time, though scientists note full recovery to pre-1980 levels is still projected to take several more decades. So far, we've covered the Sun and general cosmic rays. But there's a bigger, rarer category of threat worth addressing: powerful cosmic events from much farther away. Supernovae, the explosive deaths of massive stars, release enormous bursts of radiation. Scientists estimate that a supernova would need to occur within roughly a few tens of light-years of Earth to seriously threaten our atmosphere and ozone layer specifically. Some research has pointed to potential links between ancient nearby supernovae and past mass extinction events on Earth, though this connection remains actively debated among scientists. There's also a rarer, more extreme event called a gamma-ray burst, an intense beam of high-energy radiation associated with certain massive stellar collapses or neutron star collisions. If Earth were struck directly by a sufficiently powerful, sufficiently close gamma-ray burst, models suggest it could severely damage the ozone layer, potentially triggering serious ecological consequences. To be clear, there are no known nearby stars currently positioned to produce this kind of threat within any relevant timeframe. These remain low probability, long-term risks, worth understanding, but not something to lose sleep over. Here's the bigger picture worth sitting with. None of these systems work in isolation. The magnetosphere handles the bulk of the solar wind and charged particles before they ever reach the atmosphere. The thick lower atmosphere absorbs and scatters high-energy cosmic rays. And the ozone layer specifically targets the ultraviolet radiation that would otherwise slip through relatively unimpeded. Remove any one of these layers, and the others would be left handling a job they weren't built to cover alone. Mars is a real example of what happens when the first layer, the magnetic shield, disappears, and everything built on top of it gradually unravels as a result. Earth, for now, has all three layers intact, working together, mostly without us ever noticing. So the next time you step outside on a clear day, remember, you're standing underneath a genuinely remarkable, multi-layered defense system, a magnetic field generated deep within the planet, a thick protective atmosphere, and a thin, fragile layer of ozone, all quietly working together to make life on Earth's surface possible at all. It's easy to take for granted. It shouldn't be. If you want to keep exploring the invisible forces that make life on Earth possible, hit subscribe to Deep Space Files, because sometimes the most important science is happening right above your head.